Any questions from the homework? Emma?
Can you do 4.9, number 9?
All right. So f prime 0 equals -9. F0 equals -10. Find fx. Okay, so you know the second derivative, you want to take the antiderivative for twice to find the original fx. Every time you take the antiderivative, you create a plus c. So you end up having two constants you need to do. And luckily, you have two questions. You have two conditions for you to figure out each constant. So that's roughly the process. So number one, do it for once. You have a plus c. That will be your f prime x. Now you want to use f prime 0 equals -9. C will be -9 plus cosine 0, which is 1, so it's -8. Therefore, this will be your f prime x. Now for fx, it's the same thing. Plus a c. Again, in order to figure out c, this time you want to use this condition here. You plug in 0, you should have -10. This implies c equals -10. So fx All right, now will be number 9. Okay, Austin.
4.9, number 10, please.
A particle moves with acceleration defined by at equals 9t plus 2. Find the position st. Knowing S0 equals 1 and V0 equals -4. Okay, so this is something from physics. The first thing you want to figure out is actually the relationship between S, V, and A. S is going to be the displacement. V is going to be the velocity. Therefore, it's going to be S prime t. And finally, A is going to be the acceleration, which is going to be V prime t, which is S prime prime t. After that, you realize, okay, this is nothing but the thing we just did. We know F prime prime. You want to find the original F prime x and Fx. Moreover, you have the initial conditions. All right, with that in mind, Vt is going to be the antiderivative of AT plus a C, but now you know V0 equals -4. This implies C equals -4. So you have VT. Now you want to do ST, which is the antiderivative of VT. Again, plug in 0, you should have 1. This implies C equals 1. So finally, ST plus 1. Okay, that's how you actually do the antiderivatives. So again, you should start to get familiar with those kind of process, because usually what you do is you start from F equals ma. Okay, and then you work backwards to find V, and then you work backwards to find S. So this is usually the process in physics. Okay, you know the force, which means you know the acceleration. Then you come back and work out the trajectory. I don't know if I talk about this, but do you guys know about Kepler? Like the guy who actually figured out how the whole planets in the galaxy works, in the solar system works. Okay, Kepler. Okay. He did 3 fundamental laws by observing all the data collected by his teacher in Denmark. It's in a small cabin. His teacher just observed the whole trajectories data for 12 years, and then he died. So Kepler went there and looked at the data and figured out, shit, all the trajectory are going to be an ellipse. But then what Isaac Newton did was he started from the gravitational force equals ma. Okay, and then he take the integration for twice. He figured out the trajectory is going to be an ellipse. Okay, so he didn't collect any data. He just purely get from an equation that this is how the whole planet should be working, which is pretty amazing. So that is actually where we have the mathematical physics. Okay, so Isaac Newton just started from here, but then worked out the trajectory. So this is done by observation. This is done purely by calculation, which later developed into something called the first principle. That is, anything you do, don't trust your eyes. Okay, don't go from observations, go from the fundamental law, work out all the mathematics. Okay, then that will tell you the truth about the world, even though you haven't observed it yet. Sounds good? And that's how Albert Einstein actually developed the whole general relativity. Okay, special relativity and general relativity has been done purely in his head. He did not do any experiment. Okay, he left all the verifications to other people. We are still guided by the first principle even for now on how to do science, especially in physics and mathematics. Okay, but I think people are starting to see the limitation of the obsession with the first principle. The most recent one is actually string theory. The mathematics is so beautiful, which convince you that the world must work in this way. The sad thing is they could never verify it because the energy we need is so massive. Okay, so here's the thing. You have a beautiful theory. There's no way you can verify it is true. Even now, or maybe 10 years, 100 years later, you couldn't verify it. So what's the use of the theory? You cannot predict anything, but it works perfectly in mathematics. Okay, so that's actually what we are facing right now in theoretical physics. The whole field has been stacked for, I think, 40 years. Nothing new comes out of it. Okay, simply because people can become obsessed with the first principle. And I think recently you have more and more people doubting that should we keep pursuing this way, or should we actually go back to the old way of doing science? That is experiment first, okay, not theory first. All right. Any other questions from the homework? Okay, let's continue. Okay, the fundamental theorem of calculus. We were talking about this one last time. This is the most important thing in this class. Developed by this guy, Isaac Newton, and this guy, Gottfried Leibniz, simultaneously during the century. Okay, so let's see what this one means. We roughly talk about the idea. We said if you try to find the area from A to B, what I can do is I can actually name this one to be X and let the right end start moving. So as this X change, the whole area is going to change. Okay. After that, this one changed to here. Now what I'm asking is what's the changing rate of the area? Turns out the changing rate of the area is going to be the change of the area divided by the change of X. Okay. And if you let delta X goes to 0, which is what you're trying to do with your changing rate, eventually this one becomes super, super little tiny. And then you figure out, okay, the area divided by delta X is roughly Fx. Okay, then we have a very strong conclusion. That is the changing rate of the area equals Fx. Can you recall what we did last time, roughly? Okay. But if we have that, that tells us what? That tells us the area is going to be the antiderivative of Fx. Do you know how to find the area? Yes, Riemann sum, pain in the butt. But now you know the area is actually the antiderivative. Do you know how to find the antiderivative? Way better than Riemann sum. Okay, so now we can have a detour. If you want to find the area, you can find the antiderivative instead. That's the whole idea of the fundamental theorem of calculus. Now let's write it down in a careful way to basically just write down what we just said by words. Okay. This one has two parts. The first part looks like this. Let me make sure I copy them exactly. Okay, the first part, if f is continuous on AB, then Gx defined by is continuous on AB, differentiable on AB, and moreover, that's the most important thing, G prime X equals Fx. This Gx is called the accumulation function. Okay. What does Gx do? This is A, this is B, this is Fx. Now you change this to be X. Gx basically tells you the area of this one. Sounds good? In this way, we tell people like Gx is nothing but the accumulation of F. You can imagine a scenario like this. You have a container. You got people pouring water inside. Good so far? And the rate people pouring water inside is changing according to time. At the first hour, maybe really quick. The second hour, maybe really slow. Okay, at different time, you have a different water comes in. And that thing is quantified by Fx. Speed of the water. Or you can think about it's raining. Good so far? So what's the raining rate at 3 o'clock? That's going to be 2. What's the raining rate at 4 o'clock? That's going to be 1.5. Good so far? What does Gx do? What Gx does is actually it counts the total water inside this thing. Good so far? So for the first hour, maybe you have 1 liter per second. You did it for a whole hour. Okay, you accumulated this much. So if I plug in 1, I don't ask you what's the water flow at 1. I ask you, with all the water flow happening from 0 to 1, how much did I accumulate during that time? That will be the total. That will be the sum, not just what's happening right now. Sounds good? Okay. What do you mean by G2? G2 means what did I accumulate from 0 all the way up to 2? G3, all the way from 0 all the way up to 3. Sounds good? So can you see that? The changing rate of your G is going to be what you're pouring into the water right now. From this moment to the next moment, how much more do you accumulate? Just what I just pulled. Sounds good? Okay, so that's called accumulation. All right. To prove it, of course, it requires some careful analysis, but really, you know how to do it. You want to show G prime X is actually Fx. Let's assume you don't know it. Then G prime X is nothing but Gx plus H minus Gx divided by H. That's classic, right? Okay. But now, you know how to draw it. What is Gx? This is Gx. What is G? X plus H. This is G x plus H. All the way from A to X plus H. Good so far? So what is Gx plus H minus Gx? That's just going to be this. Because everything before will overlap. Accumulate from A to X plus H minus accumulate from A to X. That's accumulation from X to X plus H. Sounds good? What happens from 3.01 minus 3 o'clock? That's whatever you accumulated from 0 to 3.01 minus whatever you accumulated from 0 to 3. That's going to be what you accumulated from 3 to 301. Right? So that's the same idea. Just this. What is H? H is this. So now if you take this out, you got exactly what I just draw. Something like this. Okay. H and the area. So what do you want? You want this area, which is Gx plus H minus Gx, divided by this H. Moreover, you want H goes to 0. Actually, it's going to be more like this. It's still area. It's very small, but it's still area divided by H. Then can you see that? It's just going to give you the height by a rectangle. Moreover, what's that height? That height is exactly how high this is. And what is that? That is Fx. Because that's how high this is. Sounds good? Okay. So basically what we did is nothing but what we had before. You know, another way to think about it is just this. Right? You have some people. Okay? You have your Fx, you have your Gx, where Gx is the accumulation. So the first hour, what do I want to do? Let's pay you money. Okay, everybody loves that. The first hour, I pay you $2. Maybe 20. Okay, how much have you been paid so far? 20. The second hour, what do I pay you? I pay you $15. What have you been paid so far? $35. Right? Keep going. Third hour, what do I pay you? I pay you another $12. What have you been paid so far? $47. Do you see the relationship between the every single moment and the accumulation? Sounds good? So if you accumulate everything here, which means what? Which means you sum them together, you got exactly this number. That's what happens from the beginning all the way up to now. Good so far? That's number one, okay. But now if you know gx, how do you find fx? You just find the change of gx. Going from 47 to 60, how much do you change? $13. That means 13 is here. Good so far? Going from 35 to 47, how much did you change? You changed it by 12. That is gonna be what happened before until now. Do you see the relationship between them? This is very, very easy to do. So from here you can see, in economics, actually it's very easy to tell. This is called accumulation. This is called marginal. Marginal cost, marginal price, marginal supply, marginal demand, whatever. Okay, what's the relationship between them? This is actually the sum of F, right? This is actually change of G. Good so far? Okay, now imagine you still have this one, but this time you cannot have a table. You don't have the first, you have second, the third, or fourth, because I don't pay you by hour. Or I don't pay you like the first minute, second minute, third minute, fourth limit. A minute, still okay? Instead, I pay you anytime. Anytime, I pay you one. At 1 o'clock, I pay you at 1 o'clock and 1 second. Okay, I pay you at 1 o'clock and 1 second and another 1/10 seconds. You can imagine this table now become infinite many. Right? Can you still take the sum? Well, number one, if you're taking infinite many, anytime you're paying me, you pay me $0. Right? It's basically anytime you pay me $0. You pay me $2 within 1 hour. How much do you pay me every time? If you uniform distribute them, you pay me $0. Sounds good? Okay. But somehow you have a way to sum them together. What's the way? That's the way you find an area. That's the way you take the sum, by taking the integration. Now think again. When you have things just adding any time, what's the change between two consecutive accumulation? That's gonna be my changing rate. Because these two things, now the difference between them are 0. Right? You don't have the first minute, second minute. The interval between you guys are 1 minute. You don't have that anymore. The difference between you guys actually went to 0. Okay, so by that time, the change become the derivative. So this is just a limitation, not a limitation. This is just the limit of what we have here. And in real life, we do have cases where we need to accumulate things, like the case where I pour the water. I don't just, okay, open the water, do it for 1 minute, I close it. Okay, then the second minute, I do it again, right? I do it continuously. Anytime waters are coming in, right? So what's the accumulation? Well, if you just think about what's the water coming in right now, it's 0, because your time interval is so small. No matter how fast you're pouring the water, 0 water comes in. But if you accumulate all of them, now we have water. Okay, and if you think about the change of the water at any moment, it's going to be the change in rate. That will be how fast the water is flowing right now. Okay, good. With that in mind, we have this one. Very, very strong conclusion. But that's not enough. Why? Remember our goal. Our goal is try to find this. We want a way to compute this. What did you just discover? You discovered, number one, I have a function which is called gx. Number two, I know g prime x equals f. So how do you go from here to here? You just change this to b. Make sense here? All right, so what do you do? You just plug in GB. Okay. But if you want to plug in B in G, you need to know G first, right? What is G? You don't know G, but you know G prime. If you know G prime, can you find G? Antiderivative. That's how I do it. So it's settled. Two step. Number one, find the G. Number two, plug in B for X. You found GB. That will be how we do the antiderivative. Good so far? Let's see how we do it. How do you find the G? Where do you start? You start from here. If you know the derivative of G, how do you find G? I found the antiderivative. So let fx be the antiderivative of f. Good. Then gx is going to be fx plus a c. Right? What's the antiderivative of cosine x? Sin x, but possibly with another constant. Okay? How do you find gx? We need one more condition. We want to solve for c. That means we must know g. If I plug in some number, I must know exactly the number so I can solve for c. Right? Like what we did before. We know S0 equals 1, then settled. Okay, now I know I can use this information to solve C. Can you know something like that? Knowing that GX look like this? Can you somehow plug in a number and you know exactly if you plug in that number what GX is? What is GA? Right? What is the area from A to A? 0. By looking at the way we define it, we actually know GA equals 0. Can nothing help us to solve C? Of course. Then that means GA, which is FA plus C equals 0. That tells you C equals negative FA. All right, then GX, not only I know it's FX, I also know the constant C, which is FA. Now, what is this? It is GB. It is FB minus FA. So let me write it down. This will be the second part of the fundamental theorem of calculus. Very, 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 very important. Okay. There is a lot of computation, which you can figure out by yourself later. It's pretty easy to follow. You may get confused because we don't use numbers, we use A and B, right? But just keep in mind A and B are numbers. But I think the idea is pretty straightforward. Number one, you design a accumulation function. You let the final point to vary, right? It can go from all the way to A, all the way to wherever you want. Then you show that actually this Gx satisfies G prime X equals Fx. Second, if you want to find this, you just need to make sure the X become B. That means your ends at B. Okay? That's easy. The problem here is you need to do some early work to make sure that you find the formula for gx. How do you find the formula of gx? Well, you do know g prime x equals fx, so gx is going to be one of the antiderivatives. But you still don't know which one because you have a plus c there. Good news is the way you define g, if you plug in a, you should have 0. With that information, you can figure out what c is. And once you figure out that, you just plug in b. You got the whole thing. Let's try to see how we use this. Finding the definite integral from this formula, of course. Now let me remind you the painful experiences we had before and try to appreciate how much help we get from this formula. Do you remember this? Okay, do you remember we just did a Riemann sum, super long, write down everything. And I write down this and say, hey, we probably need to know how to sum all the numbers together from 1 to 100, 1 to 1,000, all the ways, flipping sum, whatever, divide by 2. Okay, that's a lot. Now forget about it. Check. Fx, A, B, right? So this one equals FB minus FA. What is f? F is the antiderivative of x. Do you know the antiderivative of x? 1/2 x squared. For both. Good so far? The only difference, for this one you plug in b, which is 1. For this one you plug in a, which is 0. Okay, now do you have it? Well, 1/2. No Riemann sum. Okay. Like we did before, this is basically the triangle. Of course it's 1/2. Sounds good? Let's try more. The second one, again, let's bring up your painful memory. We didn't do Riemann sum for this one even. This one is impossible. We need to sum all the squares together. Do you remember what we did? We tried to do this with 4 rectangles. And we did a lot of computations. It's not a good answer. Okay, it's not even accurate, but it's roughly what we can do. But now forget about it. FB, FA. What is f? F is the antiderivative of what you put here. Do you know the antiderivative of x squared? X cubed. 1/3. For both. Okay. Difference? For this one, you plug in 3. For this one, you plug in 1, which come from here and here. That's what we mean by FB minus FA. Okay, so this time it's going to be accurate. Okay, it's not an approximation. This is by mathematics. Sounds good? Keep going. The third thing we care about before, sin x which is this. No. Okay, we always say we have seen this shape so many times, right? We don't know how big it is. Number 1, we did an estimation using 3 rectangles in 5.1. Of course, that's not the right answer. Okay, the answer we got is roughly something like the pi square root of 3 or 2, something like that, right? That's certainly not a good answer. Okay, Second, we try to do the estimation. We kind of know this one is between 0 and pi, remember? It's below this. It's above that. So that's a roughly thing. I know it's between 0 and 3.14 something. Okay. Finally, this time we can do it. Antiderivative of sine. That's going to be cosine with a negative. Ending minus starting. Okay, finally. The answer is 2. Isn't it beautiful? If you ask me to guess, I would never guess a nice number like this. I would guess something with pi, right? Something like 3 point never ends or square root of 2 or something. You've never seen anything nice, any nice number like this before in trigonometry, right? Trigonometry is always like, okay, square root of 3, square root of 2, whatever you got. But this one is nice. This one is actually an integer. It's a 2. Sounds good? This is beautiful. From now on, anything like this, which you don't even want to start to do the Riemann sum, to write all of them down, to take the sum and finally take the limit, it's going to be a pain in the butt. Okay. However, from now on, you don't have to do it anymore. Every time you think about this, you just think about antiderivatives. Every time you think about antiderivatives, you think about derivatives. And every time you think about derivatives, you will be able to use everything we have so far. The first 3/4 of the class is actually trying to build the foundation for now. You can use all your old knowledge now. Okay, that's the beauty. For people who has taken calculus 1 before, you know this is the way to calculate it. But maybe you didn't try to appreciate why things work this way, because they don't have to work this way. Okay, this is beautiful. We will do more examples later, but now it's great. Everything is related to 4.9, finding the antiderivative. Okay, there's nothing better, can be better than this. Some comments before we move on. And 2 very important comments. Question 1, how do you do this? Well, you do FB minus FA. Fine. What is F? F is the antiderivative of x, okay, which is 1/2 x squared. Then automatically you know this is wrong. Why? That's not the only antiderivative. This is also the antiderivative. Actually, anything look like this is going to be an antiderivative. Sounds good? Naturally, you have a question. Which one should I plug in? Right? Should I plug in this as my fx, as I did? Or should I plug in this? Or maybe this? Try them. If you plug in this, you're going to have this. 1, 0. Okay? If you do this instead, you will have 1/2 1 squared plus 1 minus 1/2 dot 0 squared plus 1. Do they have the same answer? These two, do they have the same answer? Think again. What happened to these two with a minus? They cancel out. So even with a plus 1, and then you minus a plus 1, the plus 1 really doesn't matter anymore. It's still 1/2 1 squared minus 1/2 0 squared, right? So they have the same answer. Does it work for any constant I put there? Will they always be the same? Yes, because you're taking one of them. And will they always cancel out? Yes, because you're taking the minus. So the first question here can be answered. Just take an antiderivative. I know you have a lot of choice. Just take one. Which one you take really doesn't matter. Why? Because the only difference you can have is a constant. And these two constants, they cancel themselves. Okay, that's why when I do this, I know it's the antiderivative, but how are you sure that you can only take this, not this one plus 2, or this one plus 3, or plus pi? The answer is it really doesn't matter. Okay, so just take one. Of course, usually we take the one without a constant. If for some reason you want to use this one, that's fine. That's additional work for you. As long as you feel happy, I'm okay. Okay, but usually we just take the easiest one. So here, it really doesn't matter. And the reason is because of the plus c cancel each other. Okay, second. All right. The second thing is more about just writing. Do you kind of feel like this is ugly? Like I want all my math equation to be like everything aligned, equally spaced, and everything. Right? We actually prefer equal sign, not arrow, because arrow is kind of vague. It's like this one is roughly that, or you know what I mean, right? Usually when you write arrow, I know why you guys want to write arrow instead of equal sign. You want to say like that's what I mean. Okay, but it's not accurate. You want something looks beautiful, short, and no ambiguity. So what do you mean by this arrow here? Do you mean plug in? Or do you mean, I don't know what you mean, right? Arrow can mean anything. Okay. So can we have a better way of writing this? That's the challenge. Well, what do you need to know? Number one, you need to tell me the information that the antiderivative is going to be this. You need to tell me that, right? Second, you need to tell me what? You need to tell me who minus who. Should I plug in 1, 0, and 0 minus 1 or 1 minus 0? That's the two things you need to tell me, right? So, again, not by me, but people invented notation, which looks really nice. Number one, you just write down this. Tell people I'm doing the antiderivative. If I can do it for once, I don't want to copy it for twice. Number two, I want to tell people I have 1 and 0. So I write a big bar, tell people I have a number and another number. Moreover, the top one will be the ending. The bottom one will be the starting. So as soon as you write something like this down, people will know I should plug in 1 and the 0 into this. Meanwhile, I should take the minus. Meanwhile, the top one goes first. Sounds good? That's a notation we developed and make everybody to agree. So now let's rewrite the whole thing. This time using a different notation. That is, find the antiderivative, put 1 and 0. Once you do that, automatically you know, okay, I want to plug in 1. I want to plug in 0. I want to use a minus, and the 1 goes first. Try to look at these two ways of writing things, where I replaced everything in the right box into this. And that's a pretty nice notation, you have to say. Sounds good? Okay, so this is what I'm going to write down. 0, AB, fx dx. Basically, you just need to write down fx, b, and a. Okay, that's everything we need to know about the fundamental theorem of calculus. Okay, the key takeaway is this nice, beautiful formula. Okay, and this is done by Gottfried Leibniz. Okay. And do you know what Isaac Newton did? Isaac Newton did this. Now, with all your knowledge from the beginning to now, you know these two formulas are actually the same formula. One goes from the left to the right, the other one goes from right to the left. Sounds good? Okay, they're the same formula. Isaac Newton did it because Isaac Newton wanted to figure out the relationship between the force, the velocity. And once you know the velocity, how do you find the acceleration? Naturally, you think about the changing rate. Naturally, you think about, so this is called the work of fluxation. It's all about work of flux. Okay. Meanwhile, Gottfried Leibniz, what he did was he was trying to find the area. He was trying to accumulate all the areas. Good so far? So they approached the same formula from totally different perspective. One is trying to find the area, the other one was trying to find the changing rate. But turns out, if you accumulate all the changing rate, you got the whole thing. And if you look for the changing rate of the whole thing, you got the derivative. Okay, so they're actually one coin of two sides. It's the same coin. Good so far? So who do you think that deserve to put their name on this formula? And as far as we know, both of them. Okay, it's hard to tell who has the better contribution, even for the same thing. All right, we will do more exercise next time, but now it's time for us to see the drama between Leibniz and Newton. Basically, they're fighting for who deserve to put their name on their formula, on the formula. Can you guys see my screen? Okay, this is what happened. 1666, Isaac Newton, actually there was a pandemic. So Isaac Newton actually went to his actually farmhouse on a beautiful farm and started working there. Okay, it's very similar to what we have right now. And he started work on calculus with only manuscript. 1674, Leibniz started to work on calculus, and in 1684, he published his result as a calculus, purely from the perspective of finding the area under the curve. Okay. 3 years later, Newton published his first thing about calculus. It's just a usage of calculus. It's not the whole theory. It's just like one special case. But then another 6 years, he actually published the whole thing of how to use calculus, how to do the derivative of every single thing, like what we did in our chapter 3. Okay, how to do it for polynomial, how to do it for rational, how to do it for all these kind of things. How do you think about those kind of things, and how do you use that thing to do applications? He published everything here. Another 3 years, L'Hopital published the work and quoted Leibniz's work. So L'Hopital basically started something and said, hey, I did something based on calculus invented by Leibniz. Okay, and then Newton was pissed off. After that, they were starting a fight. The controversy began in the Royal Society, okay, of Academy. And within the next 5 years, Newton tried really hard to actually publish everything work because he wants to take the credit. He said, I need to work fast and show everybody, okay, I invented this. They all got friends. Some people take Newton's side, some people take Leibniz's side. And finally, in 1711, they went to the court. The court in the Royal Society again, okay? And Isaac Newton actually won the trial. So it seems like there is a conclusion that Isaac Newton invented the calculus, but the problem here is people question the integrity of this committee for two reasons. Number one, they think Isaac Newton won the court based on evidence provided by Isaac Newton himself. Basically, he wrote a whole thing about like how the whole thing did, but that was written by Isaac Newton himself, not any third party. Second, Newton was the chair of the committee, okay, for this trial. So basically, you are the victim, meanwhile, you are the judge. So even though you win the court, really, that doesn't say anything. And there are so many shit going on back then. So eventually people say, okay, stop it. We're going to put both of your name on it. Isaac Newton, you did from right to the left for the equation. And Leibniz, you did from the left to the right. So you guys both deserve equal credits. So this is called Newton-Leibniz formula. Okay, that's how. And people put Newton's name first because number one, it's easier to pronounce. Number two, he's a bigger name, okay, in history. So that's purely the reason why. Okay, does it worth it? From 60, I don't know. It lasted for 12 years, and actually, it even began a little bit earlier. Another 16 plus 11. That's 27 years. Okay, is it worth it? What do you think? For one formula, you spent 12 years fighting with another big name just to put your name on that formula. I'm going to tell you it's totally worth it. Do you know why? Because this is one of the most important cornerstone in human history. Okay? Did I talk about this last time? The biggest scientist in the history of human history, right? Aristotle, Albert Einstein, and Isaac Newton, who is right in between. If Leibniz end up winning, we will not have Isaac Newton to be the top three. We will have Leibniz in it. So it's totally worth it. Okay, that's probably one of the most important contribution of human wisdom, okay, in the history of human life. You know, Maxwell did Maxwell equation, which is pretty great. Dirac did all the Dirac equation with quantum mechanics, which is great. But none of them, okay, can even be compared with Isaac Newton and Albert Einstein. Okay, Aristotle is not the only one. You got Socrates, you got Plato, but they are nothing compared to Aristotle. Okay, it's just that brutal. So basically, you're talking about the top three place in the human history about science. This is worth fighting for. At least if it were me, I'm going to just fight to my death. Just say, okay, people is going to remember me forever. All the human beings from 16th century is going to remember me forever. Okay, that's worth fighting for. By the way, and Isaac Newton has a very, very interesting personality. If you want, you can Google a lot of stories about how bad a personality he has. So he's not going to let it go. Either way. All right. Have you guys heard about like Isaac Newton? A very famous saying from Isaac Newton is just like, okay, I just didn't make that many contributions. I'm just standing on the shoulder of the giant before me. Okay, that's something like, it's very humble, right? I didn't make the contribution. It's just because everybody before me, they made the whole thing. I'm just standing on their shoulder so I can look further. It sounds very humble, right? But actually, that's the thing he was. That's a phrase he used to try to mock Hooke, the guy who invented Hooke's law, because he was really short. So he's like, yeah, it seems like I'm really standing on the shoulder of a giant, because actually Hooke was really, really short, and he was mocking him using this thing. So don't trust anything you see without the context before and after. He was actually trying to mock people, not trying to stay humble. He has a really, really interesting personality if you want to hear about it. Okay, that would be all, and we will do more exercise tomorrow.